There is a clock on the International Space Station right now ticking at a different rate than the clock on your wall. Not by much, a tiny fraction of a second per day, but it is measurably, provably different. And that gap, that tiny sliver of displaced time, cracks open one of the most unsettling questions in all of science. What if space itself is not real? Stay with me here, because I'm not talking about philosophy. I'm not talking about matrix-style simulation theories or science fiction. I'm talking about a growing body of evidence coming out of the world's most prestigious physics departments, from Harvard, from Stanford, from Princeton, that suggests the three-dimensional space you are moving through right now may not be fundamental. It may be an illusion, a construction, something that emerges from a deeper reality that looks nothing like what your eyes are telling you. The proof of this starts with a clock. For most of human history, we assumed time was simple and universal, that a clock in New York, a clock in Tokyo, and a clock orbiting the Earth all ticked at the same rate. That made sense. It matched our intuition. Albert Einstein destroyed that assumption in 1905 and then destroyed it again in 1915. He showed through mathematics, tested and confirmed thousands of times that time is not fixed. Time bends, time stretches, time runs faster or slower depending on how fast you are moving and how strong the gravitational field around you is. That is not a metaphor, that is a physical fact. GPS satellites have to correct for this effect every single day. Without accounting for Einstein's relativity, your GPS would drift by several miles. The engineers who built those systems had to take seriously the idea that time runs at a different rate in orbit than it does on the ground. And it does. They measured it. It is real. Let that sink in. If something as fundamental as time turns out to be elastic, turns out to be relative, turns out to be different depending on where you are and how fast you're moving, then what else are we wrong about? And the answer that modern physics is inching toward is both extraordinary and deeply unsettling. We may be wrong about space itself. If you are watching this channel for the first time, subscribe right now and turn on notifications. What we cover here goes deeper than the headlines. We take the most important ideas shaping our world and we walk through them together carefully without shortcuts. This story is one of the most important ones we have ever covered, and it is about to get significantly more complicated. Let me take you back to the beginning of how physicists arrived at this conclusion. Because this did not start with a thought experiment about space. It started with something far more dramatic. It started with a monster, a black hole. For most of the 20th century, black holes were considered a mathematical curiosity, a strange solution to Einstein's equations. Most physicists assumed they could not actually exist. They were anomalies, artifacts of the math, not real physical objects. Then we confirmed they were real. Billions of them exist in our galaxy alone. In 2019, humanity photographed one for the first time. A black hole is a region of space where gravity is so intense that nothing, not matter, not light, nothing can escape. Around it sits a boundary called the event horizon. Cross that line and you are never coming back. Now here is where the real problem begins. In classical physics, a black hole is described by just three properties: its mass, its electric charge, and its spin. That is it. Three numbers. No matter what falls into a black hole, a star, a book, an entire civilization, the black hole keeps no record of what it consumed. It forgets everything. Physicists sum this up with a phrase that sounds almost philosophical but is actually deeply technical. A black hole has no hair. It means no memory, no record, no trace of what went in. And that created a catastrophic conflict at the heart of physics, because one of the most foundational laws in all of science states that information can never be destroyed, ever. It can be scrambled or transformed beyond recognition, but it cannot cease to exist. Think about what that means. If you burn a book, the book is gone, the words are unreadable. But in principle, if you could track every particle of smoke, every photon of light, and every molecule of ash, the information from that book is still there. It has been transformed, not destroyed. Physics guarantees that. A black hole appears to violate that guarantee completely. For a physicist, that is not an interesting puzzle. That is an emergency. That is like discovering that $2 plus $2 is $5. If information can be destroyed, then the entire logical foundation of physics, the idea that the past determines the future, that cause leads to effect, that the universe is coherent and knowable, all of it collapses. Stay with me here because this is where a young graduate student changed everything. In 1972, a 25-year-old physicist named Jacob Bekenstein noticed something. Every time an object falls into a black hole, the event horizon grows slightly larger. The surface area increases, and Bekenstein asked a question that seemed almost absurd at the time. What if that is not a coincidence? What if the information is not being destroyed? What if it is being stored on the surface, not inside the black hole, but on its boundary? This was a radical idea. Everything we know about storage says that volume determines capacity. A bigger hard drive holds more data. A bigger warehouse holds more boxes. The amount of information you can store should depend on three-dimensional space. But Bekenstein was suggesting that for a black hole, the surface, a two-dimensional boundary, was doing the storing, not the volume inside. Stephen Hawking, the most celebrated physicist alive at the time, thought Bekenstein was wrong. He launched into complex calculations specifically designed to prove it. And what he found instead became one of the most important discoveries in the history of physics. Black holes are not completely black. Hawking discovered that quantum effects at the edge of the event horizon cause black holes to emit an extremely faint radiation. They glow, barely, almost imperceptibly, but they glow. This became known as Hawking radiation, and it is so significant that it is literally engraved on Hawking's tomb in Westminster Abbey. This discovery confirmed Bekenstein's intuition. The information of a black hole is indeed connected to its surface, but it created a new, even deeper problem, because Hawking radiation means black holes slowly evaporate. Given enough time, a black hole disappears entirely, and when it does, what happens to all the information stored on its surface? That question became known as the black hole information paradox, and it consumed the greatest minds in physics for 3 decades. On one side, Hawking argued that information is simply destroyed, that the laws of quantum mechanics would have to be revised. On the other side, physicists like Leonard Susskind at Stanford and Gerard 't Hooft in the Netherlands insisting this was impossible, that if information could be destroyed, science itself would be undermined. Susskind later wrote that the first time he heard Hawking's argument, he felt a visceral unease, a physical discomfort with the implications. And from that discomfort came an idea so radical that even its authors struggled to accept it at first. If you are finding this valuable, hit that like button right now. This story is about to reach its most important turn. Susskind and 't Hooft took Bekenstein's observation and extended it to its logical extreme. Bekenstein had shown that information about a black hole lives on its surface. They asked, what if that is not a property unique to black holes? What if that is a property of all space? What if all the information needed to describe everything inside any region of space, every atom, every particle, is completely and perfectly encoded on the boundary of that region? Think about what that means. Picture your living room, the furniture, the air, the light. Now imagine that everything happening in that room could be perfectly described by equations written on the walls. Not an approximation, but a complete, perfect description. And that description on the two-dimensional walls would contain exactly as much information as the three-dimensional room itself. That is the holographic principle. And this is the moment where I need to be very careful, because this idea is easy to misunderstand. Holographic does not mean fake. It does not mean someone programmed us. What it means is that the same reality can be described in 2 completely different ways, and both descriptions are equally true. Think of a piece of music. You can experience it as sound waves or see it as notes on a page. Neither is more real than the other. They are different languages describing the same reality. The holographic principle says our universe may be like that. The three-dimensional space you move through may be one valid description of reality, and there may be another equally valid description living on a surface with one fewer dimension. Now, at this point, this was still a provocative idea without mathematical foundation. That changed in 1997. A 29-year-old Argentinian physicist named Juan Maldacena was working at Harvard when he made a discovery so significant that his paper has since accumulated more than 20,000 academic citations. When he presented his findings, theoretical physicists in suits stood up and began singing his name to the tune of the Macarena. That does not happen in physics, ever. What Maldacena found was a precise mathematical dictionary showing that a universe containing gravity could be completely translated into an equivalent theory with no gravity living on the boundary of that universe with one fewer dimension. Not approximately, but completely. Every event in the gravitational universe corresponded exactly to something in the boundary theory. And this dictionary made testable predictions. The most striking example involved black holes. A black hole in the gravitational description translates in the boundary theory into something simpler, an extremely hot, dense state of matter called a quark-gluon plasma, something physicists actually create in particle accelerators like the Large Hadron Collider at CERN. Physicists used Maldacena's dictionary to calculate the properties of black holes and then checked whether those calculations matched the plasma in the lab. They matched. The dictionary works. Stay with me here because we are now at the edge of what this actually means. If the holographic principle is correct, then space itself is not fundamental. Space would be what physicists call an emergent property, something that appears real at our scale but does not exist at the deepest level of reality. Consider temperature. When you touch something hot, that heat feels real and fundamental. But temperature does not exist at the atomic level. What exists is atoms moving quickly. Temperature is an illusion, not in the sense that it is not real, but in the sense that it emerges from something deeper. The holographic principle suggests space may be exactly the same, something that emerges from quantum information living on a boundary we cannot see. And that brings us back to the clock paradox. The clocks on the space station running at a different rate is one symptom of a universe that does not work the way our intuition insists. Time bends, space curves, and the mathematical structure points toward a reality that looks nothing like the stage we think we inhabit. Here's what I want to leave you with. First, this is not philosophy. It is real physics producing real results tested in accelerators. Second, none of this means the world is fake. Your chair is real. The distinction is between what is fundamental and what is emergent. Space may not be the most basic thing, but it is still real at the scale at which you live. Third, we have already been wrong about time. Einstein proved that a century ago, and your GPS corrects for it every day. If we were that wrong about time, we should take very seriously the possibility that we are equally wrong about space. Not because someone told us to, but because the mathematics is pointing there. The deepest question in physics right now is whether the three-dimensional space you are moving through is real in the way you think it is. And the answer increasingly appears to be probably not. We are in one of those rare moments where the map and the territory stop matching. This is not finished. Maldacena's dictionary is still being expanded to our specific expanding universe. When that work arrives, it will change everything. I will be watching, and so should you. Make sure you are subscribed. Drop a comment right now. Tell me where you are watching from and if this changed how you think about the world. I want to know how far this is reaching.